Hello guys, welcome to quantum mechanics. The purpose of this video is to find the energy of a particle in a one-dimensional box. If you recall, we found the wave equation of a particle in a one-dimensional box, right? So firstly, the Schrodinger equation of a one-dimensional box, the potential energy of that equals to zero, right? Inside the box, potential energy is equals to zero. So the Schrodinger equation will take this form to I can use the the ordinary derivative there, since we're dealing with one variable. Okay, cool. The manner in which we're going to find the energy of a particle in a one-dimensional box, we're going to use the subject of operators. I'm going to operate on a wave function. Then if I get a constant multiplied by the same wave function, then this is going to be the eigenvalue, and this is going to be the eigenfunction of the operator, So we're going to use this wave function, right? And then after we're going to apply, this will be our operator over 2m squared over dx squared. We're going to apply this operator on this wave function sine n pi over a times x, right? Okay, this equals to, first of all, we're going to factor out the square root of 2 over a, right? Square root of 2 over a. Okay. I'm going to apply this to the sine of n pi divided by a multiplied by x. All right. Let me just put this equal sign here for the sake of space. Okay, cool. All right. So this will result into this 2 over a. Okay, I'm going to differentiate this function. It's going to be the cos of n pi divided by a multiplied by x, also multiplied by the derivative of the inside function, So I can factor out this cos, it's a constant. Trust you guys can see what I'm doing. Minus a squared over 2m 2 over a n pi divided by a. Okay, so I'm gonna apply the second. I'm gonna differentiate cos of n pi divided by a multiplied by x, right? I'm gonna differentiate this. Then this is gonna be negative the sine of n pi divided by a times x multiplied by the derivative of the inside function. Okay, and then what are we left with? I'm going to factor out the negative there, so it's going to be positive. It's squared divided by 2m multiplied by n pi divided by a. It's two of them. It's this one multiplied by this one, so it's going to be that squared multiplied by the square root of 2 over a times sine n pi divided by a times x, right? Okay, I trust at this point you guys are seeing something. So it's this divided by 2m, it's n squared pi squared divided by a squared multiplied by 2 divided by a sine n pi divided by a. Okay, at this point in time, I hope that you guys are seeing what is going on. This is a constant. I can call it En. This is the same as the wave function there. So this is actually the eigenfunction, right? So what is this energy we're looking for? This is the energy, you know. So what I'm going to do now is to just simplify this eigenvalue. So our eigenvalue is the energy that we are looking for, you know, 2m n squared pi squared divided by a squared. Sorry about that. All right, so now I'm going to simplify this even further. We know that Planck's constant equals to h over 2 pi. You guys, I'm sure you given, you know, this in your data sheet or your formula sheet, you know, whatever you want to call it, over 2m times n squared pi squared. So basically it's now just a matter of simplification, right? It's now a matter of simplification. We simplify it to where we want it to be. Divide by 4 pi squared over 2m multiplied by n squared pi squared over a squared. You can say, so it's h squared divided by 8m pi squared divided by n squared pi squared over a squared. So we are almost there, guys. We can just divide this and this, and then it's h squared times n squared divided by 8m times a squared. All right. This is what we're looking for. En is equals to h squared n squared over 8m a squared. So what is this? This is the energy of a particle in a one-dimensional box, right? And it is worth noting, guys, that this energy can take, you know, discrete values, right? It is quantized, basically. The presence of n, which is a quantum number, you know what I'm saying? So this energy, guys, is quantized. It can take, you know, discrete values, right? All right, so we have arrived at our final equation. So yes, thank you guys for watching. Just write down any questions that you might have in this equation. I'm also gonna write a question for you guys, you know, in the description section, and hopefully you will get it right. All right, stay cool, guys.